Okay, so now we're in 11.3. We're talking about the integral test, and we're looking at some estimates for sums. From here on through the next few sections, we're going to be looking at different types of convergence tests. So far, we've only looked at a couple of different ways that a series can converge, a couple of different techniques for testing that. One was telescoping series. So those are the types of series where when you take several of the partial sums, you're seeing a lot of cancellation happening in a way that like leaves you with only the first and last term in that partial sum. We did one example like that. So those are one type of series that converge, and it's not hard to see why. Another thing we looked at was geometric series. Those geometric series that had a common ratio whose absolute value was less than 1. Those guys always converge. And those show up pretty often. So that's one that we're going to use over and over again throughout this chapter. But those two tests are very restrictive. Most of the series we look at don't fall into either category. So we need more tools for determining whether or not a series converges. The tool we're talking about here is called the integral test. And so to motivate it, I want to look at this specific series right here. The series as n goes from 1 to infinity of 1 over n squared. It's not a geometric series, and it's not a telescoping series, so we can't apply either of those techniques here. But there is a way of comparing this series to something we've already talked about lots in this class, which is integration. So what I'm going to do is define the function f of x to equal 1 over x squared. And that's going to be a function of real numbers, not just natural numbers. So I could graph that. I know that the graph of this thing, if I look at just the part of the graph that lives in the first quadrant, would be like this blue curve right here. Okay? The next thing I want to do is approximate the area under this curve using rectangles. And specifically, I'm going to use rectangles with right endpoints. So this first term right here, if I'm plugging in right endpoints in these subintervals, and if I make my subintervals if I make my subintervals have a width of 1, so I have an interval from 0 to 1 here, an interval from 1 to 2, 1 from 2 to 3, and so on. And if I let this go indefinitely, so all the way on down, approaching infinity, and I find rectangles under that have each of those subintervals as a base, and the right endpoint of each of those subintervals is plugged into the function to give me the height of this rectangle, then the height of each one of these rectangles is equal to 1 over whatever that number is squared. So 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. Because the base of each of these rectangles is equal to 1, the area is just the height times the base. And multiplying something by 1 doesn't change it. So this area would just be equal to 1, and this would be equal to 1 over 2 squared. This would be equal to 1 over 3 squared, and so on and so forth. Okay? Now, I can interpret the terms of this series right here as the areas of these individual rectangles, not counting this first one, because if you notice, this series goes from 1 to infinity, so we're not going to use that first rectangle, but starting here, my first term in this series would be 1 over, oh no, I'm sorry, I said the wrong thing. 1 over 1 squared is this first rectangle, so yes, we are going to use that. 1 over 2 squared, that would be the second term of this series. It's also the area of this first rectangle. 1 over 3 squared, that'd be the third term of this series. It's also the area of this third rectangle. So that this sum represents the combined area of all of these infinitely many rectangles down here. Okay? Now, the actual area under this curve, if we go from 1 to infinity, that's an improper integral. I can see that if that area is finite, it's going to be greater than the combined area of all of these rectangles, not counting this first one. Because again, we're going to go from 1 to infinity here. So if that, what that means is that if the improper integral of 1 over x squared from 1 to infinity is finite, then whatever number that is greater than the sum of this series, but that implies that this series also adds up to something finite, which would mean that it converges. So we can evaluate that here. The combined, or the area under this curve would be the improper integral from 1 to infinity of 1 over x squared dx. And the extra term here that we're not counting gets added to that, so that this thing is a number that's larger than the sum of my series. So this thing is larger than the sum of my series. This improper integral we have evaluated back in chapter 7. We looked at improper integrals. It comes out to just 1. So this is 1 plus 1, or 2. Because this is finite and the sum of my series is necessarily less than this, then my series must also converge. By using that integral, we just showed that this original series right here is convergent. Okay. Now don't get thrown by this number here. This is not what the series sums to. The integral is not being used to show what the limit of this series is. It's just confirming that it converges. And that's an important distinction, because sometimes you can show that a series converges by finding its limit. Other times we can show that a series converges without finding its limit. In fact, finding the limit of a series or the sum of a series can be very, very difficult in some cases, even if it's not that hard to show that a limit exists. So that's all that we've done here. Now, to be a little bit more precise about how we know that this series converges here, the terms of this series, let's go back up here. The terms of this series are bounded. Notice each of these terms is necessarily less than or equal to 1, but they're all positive. They're all greater than 0. So that means that this sequence of terms is bounded. In addition to that, the sequence is decreasing. Every new term is smaller than the one that came before it. So it's a bounded monotonic sequence because it's decreasing, and by the monotonic sequence theorem, that is going to be a guarantee that this series converges. We talked about that back in 11.1. So that's the more precise way of guaranteeing that we have a convergent series here. Now let's use a different example. Let's consider this series here, where we go from n equals 1 to infinity of 1 over the square root of n. We're going to do the same thing, but this time we're going to approximate area under a curve using left endpoints. So to find the function y equals 1 over the square root of x, which, remember, that's going to agree with the terms of our series for any positive integer value that I plug in for x there. And then if we use left endpoints on each of these subintervals of width 1, this is what those rectangles would look like. So this rectangle, I'm plugging a 1 in, I get 1 over the square root of 1 times 1. So 1 over the square root of 1 is the area of that rectangle. Then I plug in 2 for this left endpoint. 1 over root 2 ends up being the area of that rectangle. And then 1 over root 3, and so on and so forth. These are the terms in the series that we're looking at. And notice this time, because I have a decreasing function and all of these rectangles are using left endpoints, the combined area of these rectangles has to be greater than the area under the curve, because each rectangle has a little extra area up on top there. Okay, so if I were to look at the improper integral from 1 to infinity of 1 over the square root of x, that would give me the area under this curve from 1 to infinity. But we know from chapter 7 that this improper integral diverges to infinity. So that means that this series, which has to have a greater sum than this improper integral, also has to be carried to infinity. It can't be finite. So to generalize the idea that we're using here, we have this thing called the integral test. Suppose that f is a continuous, positive, decreasing function on the interval 1 to infinity, and let a sub n equal f of n. So this is saying that this is going to end up being the terms of our series, and the terms of our series will agree with this function for all integer values that we can plug into it, all positive integer values. Then the series from this series here is convergent if and only if the improper integral is convergent. So in other words, if this integral is convergent, then so is the series. If this integral is divergent, then so is the series. So that's essentially summarizing or generalizing what we just did in these two previous examples. It's important to pay attention to the conditions that have to be in place in order to use this. We're using a function of real numbers to model the terms of our series after. And that function has to be continuous. All of its values have to be positive, and it has to be decreasing all on this interval right here. That was the case for both this function and the 1 over x squared function previously. It was continuous, it was decreasing, and it was positive. All of its terms were positive on that interval there. Okay. I mentioned here that if we can prove this theorem more rigorously, and we do in the textbook, but we're not going to go through that proof here. We're going to just use the argument that we showed with those previous examples to kind of intuitively understand why this works. But let's look at an example. Determine whether this series 1/5 plus 1/7 plus 1/9 plus 1/11 and so on is convergent or divergent. Okay, so what I want to do is find a function such that when I plug 1 into my function, I get 1/5. When I plug 2 into my function, I get 1/7. When I plug 3 into my function, I get 1/9, and so on and so forth, like that. And I need to make sure that the function that does this is positive, decreasing, and continuous on the interval 1 to infinity. So there's different functions I could find that do this, but if we look at some patterns here, I can see that I always have a 1 in my numerator, and then I can also see that this term or this number in the denominator is increasing by 2 each time. So that suggests that I should use a 2x down here plus something to make sure that I have the correct first value. So again, if I plug a 1 into this, I'm going to get a 2 times 1 down here, which is 2. It should be a 5. So by adding 3 to that, I can go from a 2 to a 5. Verify that we get these other values as well. If I plug a 2 in, 2 times 2 plus 3 is 7. Plug a 3 in, 2 times 3 is 6, plus 3 is 9, and so on. So this thing will give me all the correct terms. Okay. Now what I need to do is confirm that this thing satisfies the criteria that it's supposed to. Are all of these terms positive on this interval? Well, they are, because if I plug a positive number in for x, then I have a positive denominator. That's easy to verify. Positive 1 divided by a positive number is always going to be positive. Is it a decreasing function? Yes. As x gets bigger and bigger, then this denominator gets smaller and smaller, so that this function is decreasing. Finally, is it positive? Or no, we said that already. Is it continuous? Yes, it has a discontinuity only where x is equal to -3/2, because that would put a 0 in my denominator. But -3/2 is outside of this interval, so it doesn't matter. It's okay that it's discontinuous on numbers outside of that interval, as long as it's continuous in that interval. So this hits all of those criteria. Now we need to evaluate this indefinite integral, 1 over 2x plus 3 dx. So you remember, we evaluate improper integrals by converting them into limits of this form. Limit as t goes to infinity of 1 to t of 1 over 2x plus 3 dx. Okay, now this guy, limit as t goes to infinity, this is equal to 1/2 times the natural log of the absolute value of 2x plus 3. Again, from 1 to t. All right, the 1/2 I can just pull out here, and I have the limit as t goes to infinity of the natural log of 2t plus 3 minus the natural log of, I'm plugging a 1 in, so 2 times 1 plus 3 would be 5. Okay, I didn't use the absolute value bars because if t is approaching infinity, then this thing is going to be positive anyways, so I don't need to worry about taking the absolute value of that. I know that the natural log function goes to infinity as its argument goes to infinity, and as t goes to infinity, 2t plus 3 will also do that. So this is going to go to infinity, and subtracting a finite number from that won't matter. So this is infinite. Because my improper integral diverges to infinity, then my series also diverges by that integral test. So I can say that the series diverges.